So now we're going to talk about finding the moment of inertia of a cylinder. And specifically, we're thinking about cylinders with the axis that goes right through the center right now. So this kind of axis, this kind of cylinder will have some length, capital L, and some radius r. Now, first, we'll take the easiest case, hollow cylinders. So our equation for the moment of inertia is going to be an r squared dm integral. So for a hollow cylinder, every single particle of mass is exactly r away from that axis. So then I bar of a hollow cylinder is going to be r squared times the total mass m. Done. It's a little bit more complicated if it's solid. If it's solid, then some of the mass has distance r, the sum of the mass has distance less than that, because it may be, and some of the mass has no contribution. The mass right here at the axis would have no contribution to the moment of inertia at all. So we have to do an integral, and so we're going to integrate the r squared term for every mass in our cylinder. And we can look at the masses in kind of this framework, right? So each section of our cylinder that has some radius r and some arc length d theta is this little tiny, like almost rectangle. And that rectangle would have some little differential area. And then the mass of that little differential piece, the little differential mass, is going to be proportional to that little differential area by the ratio of the total mass to that area, if the density is constant. And so then we know the total area of a circle is pi r squared. And so we have our total mass. And then this little area, we can just treat it as a little rectangle in the differential sense, where one side length is equal to the arc length, which is r d theta. And then the other side length is our just little differential r. Okay, so now we can substitute our expression for our differential mass right in here in our integral. So now we're taking the integral of r squared times our little differential mass right here. Right? Now it looks a little bit more complicated, but it's not too bad, because we're just going to move this term as it's constant, it's not changing with our theta or our r, we'll move that right outside the integral. And now we can start with taking the integral over theta, and so we want to go from, for our theta integral, we want to go from 0 to 2 pi. That's the limits of our integral, because we got the whole ring, right? And we want, then for our r integral, we want to go from 0, like no radius, to the outer radius, big R. And let's just do the theta one first. It doesn't matter which order you do this in. Like if you do it, the theta first, it's like you're integrating a bunch of little rings, nested rings. And if you do the r first, it's like you're adding up a bunch of pizza slices. So let's do our theta first. So when we integrate that, there's actually no theta expressions in here, so that's really easy. The integral is just 2 pi. So we'll bring that 2 pi outside here, and then we'll multiply, we'll bring this stuff outside the integral too, because it's all constant. And then we'll take the integral from 0 to r of everything that depends on r, which is just r cubed dr. So then that brings us to get r fourth over 4. And now look, things start to cancel out. This r, the quadratic, or the r to the 4th, divided by r squared is going to give us r squared. The pi's cancel out. This 2 and this 4, you just get 1/2. So now this is going to be, for a solid cylinder, our moment of inertia is r squared over 2. And so you see that it's good that it's less than the hollow cylinder. If you have a hollow cylinder with a mass m, all of that mass is far away from the central axis. So that makes sense that that has a little bit more difficulty to rotate that, to accelerate, like rotationally accelerate that. And if it's solid, then some of it is easy to rotate because it's close to the center. And the other thing to point out is that this length L, when you're looking at a cylinder head on and you're rotating it about its central axis, doesn't matter, right? It doesn't matter if it's like a thin coin that you're rotating about its center, or like a really long pipe. Just matters the mass distribution. And so there we go. Thank you.